As some of you may have noticed, there are a lot of patterns that happen with quadratic functions. Let's look at the most basic pattern in the parent function of y equals x squared. So when we have our table of values for this parent function, we usually have our inputs of -3 to +3. So let's just go ahead and fill those in. -3 squared, 9, and 9. By now we've seen these quite a few times. Over on the graph here, we have our vertex at 0, 0. That's the most basic vertex. And then we always go to 1, 1 and -1, 1, 2, 4 and -2, 4, 3, 9 and -3, 9. So you might notice that there's always this same pattern that happens. If I started at the vertex, every time I move 1 away in either direction from that vertex 0, my change is an increase of 1. If I move 1 to the right, I'm also moving up 1. If I'm moving 1 to the left, I'm also moving up 1. That's because squaring 1 produces an output of 1. But what happens when I move 2 away? Our change is adding 4. And in the graph, you can see that as I move 2 away from the vertex, my increase jumps all the way up to 4. Move 2 away in the other direction, increase of 4. That's because when we square our input of 2, our output's 4 in either direction. What happens when we move 3 away from the vertex? Well, 3 squared is a change of 9. So our change here would be 9. So again, starting at the vertex, as I move 3 away, my change is +9 in either direction. 3 to the left, change of +9. So how can we use this to get better at graphing quadratics so that we don't just have to plug in these tables every time and evaluate? Let's look at a few examples. So hopefully you just completed a Desmos warm-up, in fact 4 warm-up questions, where you had to complete tables and parabolas for 4 different functions. Now this probably took quite a bit of time because you had to sit there and plug in all these x's to generate your y's, but how would you feel if you could do this a little bit faster? So in warm-up number 1, we noticed that our parabola had a shift to the left 2 units and down 4 units. However, did it undergo any type of dilation or reflection? No, because in this case, there was no multiplier, there was no coefficient here. If anything, this was a coefficient of 1. So it didn't undergo any type of dilation, which means that there's actually a pattern here that we could have used to complete the table. Let's review the pattern that we notice in the parent function. As I start at the vertex, if I move 1 away in either direction, my change is going to be a +1. And if I move 2 away in either direction from the vertex, what's my change? +4. Starting at the vertex here, what's the change as I move 1 away in either direction? Well, -4 plus what is -3? That's a change of +1. We can see the same thing in the graph. As I move 1 away, that change is +1. What about as I move 2 away from the vertex? What's the change from -4 to 0? That's a change of +4. And in the graph, moving 2 away shows me that same change of +4. So really, we can say that this parabola, we can tell that this parabola has not been shrunk or stretched because it still has that same pattern as the parent function. And we can actually use this to graph it in the future. Do we observe the same pattern in warm-up 2? Well, let's see. Starting at the vertex, in both the graph and the table, as I move 1 away, what's my change? 2 plus 1 is 3. And we can see that in the graph as well. 1 away, up 1, 1 away, up 1. As I move 2 away from the vertex, my change is 4. 2 plus 4 is 6. 2 plus 4 is 6. And in the graph, we can see that as well. 2 away, up 4. 2 away, up 4. So again, we know that this graph did not undergo any type of stretch or shrink because it has the same pattern in the outputs as the parent function. So really, we could have used this pattern to graph from the beginning. Then we hit warm-up number 3. This one doesn't seem to have the exact same pattern, but it has something close to it. Let's observe. Here's our vertex output of -6. Here's our vertex right here. As we move 1 away from the vertex, what is the change here? -6 plus 2 is -4. And we can see that in the graph as well. 1 away is now an increase of 2, whereas before that increase was only 1. What about our 2 away change? As we move 2 away from the vertex, 2 units away, that's a change of positive 8. Negative 6 plus 8 is 2. Negative 6 plus 8 is 2. And in our graph, we can see the same thing. As we move 2 away, 8 is our change. And in our parent function, the normal change would have been 2 and 4. So we went from a change of positive 1 to a change of positive 2, and from a change of positive 4 to a positive 8. The reason why our outputs are different here is because we multiplied our parent function by a factor of 2, meaning we stretched it by a factor of 2. Now, isn't it interesting that our normal pattern is 1 and 4, and our new pattern here is twice that. 2 times 1 is 2. 2 times 4 is 8. So really, this has the same idea in pattern, except for it's twice the distance, because again, that change has doubled. Interesting. Well, then what happens here with warm-up number 4? Because this one underwent many changes. Let's see. Here's our vertex. Let's first look at the change that's 1 away from the vertex. How do we get from 8 to 4? That's a change of minus 4. So in our graph, we see as we move 1 away, that's a change of down 4. That means that's how we can tell that it's a reflection. 2 away, starting at 8 and ending at negative 8, is a change of negative 16 or minus 16. In the graph, we can see the same thing. 2 away, our change is all the way down negative 16 units. 2 away, go all the way down 16 units. This graph underwent a stretch by a factor of negative 4. In other words, A here is negative 4, the number that's out in front, the coefficient. This is significant because we took that pattern of 1 and multiplied it by negative 4. And we took that pattern of 4 and also multiplied it by negative 4. This has the same pattern of 4, 1, 0, 1, 4, but now it's multiplied by negative 4, causing it to be negative 4 times than the parent function pattern.